Morning everyone. In this video, we shall continue discussing the topic of aromaticity. In the previous video, we have already discussed the meaning of the phenomena of aromaticity, the requirements needed for a compound to be aromatic, their nomenclature, and their reactions, and we said that they can react by electrophilic substitution reactions and nucleophilic substitution reactions. We specified that nucleophilic substitution reactions are quite rare and they need a very strong electron withdrawing group on the ring to be performed. Then we started discussing the electrophilic substitution reactions, and we mentioned that there are 4 types of electrophilic substitution reactions. We said that they are the nitration, sulfonation, halogenation, and the Friedel-Crafts reactions. Friedel-Crafts reactions were divided into the alkylation and the acylation of a benzene ring. We discussed the mechanism of such a reaction and how to form the electrophile. Finally, we explained the different limitations that can face us while performing a Friedel-Crafts alkylation reaction. Today, we will continue discussing the electrophilic substitution reactions. However, we will discuss the introduction of a second substituent to an already substituted ring. Which positions will the substituent go to? In the previous video, when we introduced a substituent to the ring, we had all positions of the benzene equivalent. This one was equivalent to that one, to that one. There was nothing to specify a specific position. However, now when we have a substituent on the ring, we have different positions. We have, as we mentioned, an ortho position, which is the position immediately adjacent to the carbon carrying the substituent. If we skip one carbon and we move to the next, this is the meta positions. And finally, the position on a straight line from the substituent, this is the para position. Already in the previous video, we have mentioned that electron donating groups will direct to the ortho and para position, while electron withdrawing groups will direct to the meta position, and we did not specify the reason for this. Today, we will explain the reason for such orientation. Regarding electron donating groups, they are donating, which means that they give electrons to the ring, whether by induction or by resonance. And since we are actually performing an electrophilic substitution reaction, which means that we are introducing an electrophile, which means that we are introducing something devoid of electrons and needs electrons, then the more electrons present in the ring, the easier the reaction. So it's very easy to introduce a second electrophile to a ring that is already carrying an electron donating group. On the other hand, if the ring contains an electron withdrawing group, then this means that this ring is not rich enough in electrons because it's already carrying something which is withdrawing the electrons, something taking the electrons away from it. And since we are introducing something that needs electron, then this reaction is more difficult than introduction of the electrophile to an unsubstituted benzene ring. So this is an easy reaction. The electron donating group presence on a ring makes the reaction easier. The presence of an electron withdrawing group on the ring makes the reaction harder. And as we mentioned, this category will direct the new electrophile to the ortho and para positions, which means that your electrophile will be introduced to these positions. and in this case your electrophile will be directed to the meta position, which means that your electrophile will be directed to these positions. Let's try to discover why would an electron donating group direct the new electrophile to the ortho and para positions, and why will the electron withdrawing direct them to the meta positions. If we have a ring and it has a substituent, and this substituent is an electron donating group, which means that this substituent already has electrons that it is giving to the ring. If we perform this resonance, we will notice that the negative charge will be moved to the ortho position. You have, as we mentioned before, how do we run a resonance in a ring? You name or you number the atoms. This is atom 1, atom 2, and atom 3. You will consider the electrons as if they are a charge, whether they are a lone pair of electrons or a negative charge. As we have mentioned in other videos, the resonance involves the movement of the electrons or the charge from atom 1 to atom 3 and an exchange between the single and double bond. A resonance is a process that takes place between 3 different atoms and 2 bonds. You have atom 1, atom 2, and atom 3. Atom 2 of which have a double bond in between, the other 2 have a single bond, and the terminal atom having the single bond will have a negative or a positive charge or a lone pair of electrons. The charge moves from atom 1 to atom 3, and an exchange of single and double bonds between the 3 different atoms takes place. To explain this in chemistry, as in terms of electrons, what we say is that this atom, the Z atom, the atom number 1, has a charge on it. So it gives these electrons, it has electrons, excess electrons. It will give these electrons to the atom 2, to atom number 2, so that it can use them to make a double bond between the Z and the 2. This way, the 2 electrons on the Z will be used to form a double bond between 1 and 2 atoms. Now 2 is carrying too many bonds, more than it can tolerate, so it has to break one of the bonds around it. It breaks a pi bond. It cannot break a sigma bond in resonance. It breaks a pi bond. Breaking the bond means that it will give all the electrons of the bond, both electrons, its electron and the electron that already belonged to atom number 3, to atom number 3, creating a negative charge on atom number 3. So this is how a resonance takes place. Let's draw the resonating structure. As we have said, you will exchange the single with the double. So between Z and 2, you had a single, it will be a double. Between 2 and 3, you had a double, it will be a single. And the charge will move from atom 1 to atom 3. So let's apply this to the structure that we have already been dealing with. As you see, the single and the double were exchanged, and the lone pair of electrons, or the negative charge, has been moved from atom 1 to atom 3. Let's do the same. Again, you will move let's number them. This is atom 1, 2, and 3. So let's draw the new resonating structure. You have the double bond Z, you have the double bond on the left side, you did not touch it. And now let's move the charge and the double bond. You had a single bond between 1 and 2, so now it's a double bond. You had a negative charge on 1, you will move it to 3. Let's run the third resonating structure. And then finally, you go back to the same structure you had, which is the Z carrying either the lone pair of electrons or the negative charge. Okay, so this is how your resonance will go, or how your resonance will proceed in case of an electron donating group. Let's look at the structures or the resonating structures that we have obtained. We will find that position 1, the ortho position, this position, the ortho position here, the para position here, and the other ortho position here are carrying a negative charge. And since we are introducing an electrophile which is looking for a negative charge, so it will prefer the positions that did carry a negative charge. It did carry electrons, which are the ortho and para positions. Carrying a negative charge means that they are much richer than any other position in electrons. So this is why the electrons will be directed to these positions, the ortho and the para positions. However, if we have an electron withdrawing group on the ring, which means that this position is probably, or this substituent is probably carrying a positive charge or a partial positive charge, then this position is actually attracting electrons from the ring. Let's run the resonance. If this is atom 1, 2, and 3, let's exchange the charges and exchange the single and double bonds. Now you have a double bond between the ring and the electron withdrawing group, and you have a single bond between atom 2 and atom 3, and atom 3 now is carrying the positive charge. Let's continue the resonance. This is 1, 2, and 3. Let's continue the resonance. You have the electron withdrawing group, the double bond on the left, we did not touch it. We are exchanging now the single with the double, and we are moving the charge. Let's run another resonance. And finally, you go back to the starting structure. Let's look at these structures. You will notice that the ortho and the para positions are the positions that carried a positive charge. What does a positive charge mean? It means that this position is devoid of electrons. It does not have electrons. Its electrons have been taken away from it. So definitely, if I'm introducing an electrophile which is looking for a negative charge, it's looking for electrons, it will try to avoid the positions that carried the positive charge. And that's why your electrophile will never go to the ortho or the para position. It will directly go to the position, the only position that did not carry the positive charge, which is the meta position. So to clarify here, your electrophile did not go to the meta position because your electron withdrawing group activated the meta position. This is not true. Your electron withdrawing group did not activate the meta position. However, it deactivated the ortho and the para. So the electrophile had no choice except to go to the only position that was not deactivated, which is the meta position. Now let's discuss a strange substituent, a very different substituent. We have the halogens. What are the halogens? These are we always denote them by an X, and these are the chloro, fluoro, bromo, and iodo substituents. Okay, so if we have a halogen on a ring, is it an electron donating group or is it an electron withdrawing group? Halogens, despite the fact that they have a lone pair of electrons and they should act as an electron donating group by this lone pair of electrons in the form of resonance, this is not true, and they do not do this. What they do is that they are highly electronegative atoms, so they actually act as electron withdrawing groups by induction. They withdraw electrons from the ring by induction, and they do not give their lone pair of electrons to the ring by resonance because of their high electronegativity. This prevents them from giving their electrons by resonance. They only withdraw by induction, and they do not give by resonance. Okay, so they are electron withdrawing groups. So I should expect them to direct the new electrophile to the meta position. My expectations is that they should go to the meta position. The second substituent should go to the meta position, which is not true. Your second substituent will be again directed to the ortho and para. So how come? Why are they directing to the ortho and para position even though they are electron withdrawing groups? Let's look at the resonance that will take place. First, before looking at the resonance, what actually happens here? What happens here is that it's true that these groups or these atoms will not give electrons by resonance in regular or natural cases. In such a case that you already have drawn, they will not give these electrons. However, if the halogen is attached to an atom that is carrying a full positive charge, not a partial charge, it has to be a full positive charge, this is the only condition when the halogen will give its electrons by resonance. It's as if a person has money, but he's a cheap person. He does not like to give his money. So if he sees a person in moderate need of money, he will not give him anything. However, if he sees a person almost dying out of hunger and does not have any money and does not have any food and did not eat for days and is probably gonna die within an hour or 2 hours, he will then give him money. He's a cheap person, but he's not that cheap. So he will give money when the situation is desperate. So this is actually what happens. The carbon directly attached to the halogen has to carry a full positive charge to force the halogen to give the electrons by resonance. So the electrophile, while entering to the ring, really wants electrons. The more the electrons it can get, the more the electrons present on the position it will enter, the better for the electrophile. So the electrophile starts looking for a trick, how to trick the halogen, to force the halogen to give its electrons to the ring by resonance. What is this trick? It's to choose the correct position to enter which will force the halogen to give the electrons. What the electrophile is doing is that it's looking for the position. If it enters, if we have this as the electrophile, it has two options. It's either to enter the ortho or the meta. Let's look at the ortho and the meta, and the same applies for the para and the meta, which will be then these two together. You are looking for a double bond that you need to break. You will break it in the direction of the ortho position to put the negative charge on the ortho, or you will break it in the direction of the meta to put the negative charge on the meta, so that it will attack the electrophile. The electrophile is now choosing between position 1 and position 2. It's trying to decide which position will have more electrons. And it knows that the substituent on the ring is a cheap substituent. It's the halogen, the one that does not give its electrons easily. We need to trick it. We need to force it. So we need to find the position that will put a full positive charge on this carbon. The carbon immediately attached to the halogen. If it's an adjacent carbon, the halogen will never help it. It does not mean anything to him. This is not a close person. This is a faraway person, so they can go and die. It's not his problem. The problem is that the person directly attached to him, the person staying with him in the same room. This is how to describe it. It's like the brother who's staying in the same room with me. I have to help him if he's dying. Otherwise, if it's someone in the next room, I do not care. So we need to put a positive charge on the carbon directly attached to the halogen. So the electrophile will start trying by its eyes. It will look on both positions and try to determine or try to predict which position will put a positive charge on this carbon. Okay, so it will try both. Let's try. position 1 if the halogen, if the electrophile was introduced to position 1. So now you have the electrophile, you have the hydrogen, and you have the positive charge here. And now you have the other double bonds, so you will run a resonance. And now you have the positive charge here, and then another resonance. And now you have the positive charge directly on the carbon, directly attached to the halogen. So this is a very preferable position. Let's try the 2 position. This is the halogen. These are my double bonds, and now the the electrophile was introduced to the meta position, and the ortho position is carrying a positive charge. Let's run the possible resonance. The positive charge jumped the carbon that is carrying the halogen and moved to the other ortho position. So this is not preferable. Going to position 2 or going to the meta position is not preferable to the electrophile, because in this case the halogen is not forced to give its electrons by resonance. This halogen will not give its electrons by resonance, because the carbon immediately attached to the halogen did not carry a positive charge. If you want to run this on the para position, we have this and that position, the para versus the meta. So now let's consider this 1 and this 2. Let's run the 1. This is your halogen. You have these double bonds. Now you have introduced the electrophile to the 1 position, and the 2 position is carrying the positive charge. Let's run the resonance. As you see, again, the positive charge jumped the carbon that is carrying the halogen and moved from one ortho position to the other. Let's try the 2 root. As you see, you have placed a positive charge on the carbon directly attached to the halogen, so the halogen will have to give its electrons by resonance to the ring to help the adjacent carbon. So this is why, even though halogens are electron withdrawing groups, they will direct the new electrophile to the ortho and para positions. I need you to remember one word here, which is that you will never be able to place a charge on the meta position during a resonance. If you are performing a resonance related to a specific group, you will never be able to place a charge on its meta position. It always places the charges on the ortho and para positions. This is because you are always jumping atom number 2 in a resonance. If you remember, we said that a resonance involves atom 1, 2, and 3. The charge moves from 1 to 3, so you are always jumping the 2 position, which is always the meta position. You will never be able to introduce a charge, whether positive or negative, to a meta position of the ring. Okay, so this is when you are introducing a second electrophile. Suppose now that you have a third electrophile that you need to introduce. You will have to choose between the 2 substituents that are already present on the ring. You already have 2 substituents on the ring. What are these 2 substituents? they could be both are electron donating groups, or one electron donating and the other is electron withdrawing, or they can both be electron withdrawing groups. According to the nature of the substituents, the third substituent will be introduced. The third substituent again is an electrophile, so it is actually looking for electrons. So let's look at the second case. If one is electron donating and the other is electron withdrawing, then it will definitely prefer to be directed according to the electron donating group, because this is the group that is actually giving electrons. So this group is putting a negative charge on the ortho and para positions of itself. So it's looking for the positive and negative, it's looking for the ortho and para positions of the electron donating group, and it will go to them because these are the positions that are actually carrying a negative charge. So this is very easy to determine. The problem is with case 1 and 3. If both groups are electron donating groups, where will the electrophile go? And if both groups are electron withdrawing groups, where will the electrophile go? Let's look at the first case. Both are electron donating groups. If both are electron donating groups, it's like, let's imagine a situation where when I go in the morning to say good morning to my father, he will give me an allowance of $10. And if I go to my mother, she will give me an allowance of $1. And if I go to my brother, he will ask me to give him an allowance as an older sister of a $1. Which do I prefer? Or who do I prefer? My father, my mother, or my brother? Who will I run towards in the morning? As soon as I wake up, who will I go to say good morning? It will be my father. He will give me $10. If my father left earlier before I woke up, and I do not have the father in the house now, I only have the mother and the brother, who will I go to? I will go to my mother. It's true she only gives $1, but still she gives me something. It's not like I'm not going to get anything. So I will go to my mother first. If my mother is not in the house, I will not go to my brother. I will not prefer to go to my brother because he will actually ask for an allowance from me. This is, of course, if I'm a cheap person. And usually an electrophile is a cheap person because he does not have money. He is already carrying a positive charge. Electrons are like money in chemistry. If you are carrying a positive charge, this means that you do not have money. You are actually in debt. Your money has been stolen, your allowance has been stolen, and you need someone to give you extra money to make up for the stolen electron. So this is how electrons are regarded if you are trying to describe them in terms of real life. So now, if I have on the ring an electron donating group and another electron donating group, and the electrophile is choosing, it will choose the one which is donating more. For example, one of the donating groups has a negative charge while the other has a partial negative charge. Definitely the one having the negative charge is donating by higher ability or higher capability than the one just carrying a partial negative charge. So this is a stronger electron donating group. It will definitely choose, this is my father, while this is my mother. This is the weak donating. It's a weak donating group. Still donating, but it's a weak donating group. So definitely the electrophile will choose to go to the ortho and para positions of the stronger electron donating group. So this is the case when both are electron donating. If we look at the second case, one is an electron donating and the other is an electron withdrawing group, then the electrophile, this is exactly like my father and my brother. Definitely, I will not choose to go to the positions of my brother. These are positions that are divides of electrons. So instead, I will look at the positions where my father is orienting, and I will go to them, which are again the ortho and the para positions of the electron donating groups. Now, if both are electron withdrawing groups, I will try to avoid the positions where these put a positive charge. So I will try to avoid the meta position of this group. So I will avoid these, and I will avoid the meta position of these. So now I have all the ring blocked. How do I act now? I will have to do one of two things. It's either the reaction will not proceed because the ring is carrying strong electron withdrawing groups and several strong electron withdrawing groups. So this reaction is a difficult reaction. It might not proceed. And if I force it to proceed, it will look for the position that is the meta position of the weakest withdrawing group. Now I need the group to be weak withdrawing, not strong, because if it's strong, then it's placing a full positive charge, a very high positive charge on the position. So this is how the groups are oriented. We will see examples in a moment in the organized slides. So looking at the organized slides, as we have mentioned, we have either the possibility of an electron donating group on the ring or an electron withdrawing group on the ring. As we said, the electron donating group will increase the electron density, facilitating the reaction, while the electron withdrawing group will increase the electron density, making this reaction difficult. As we have mentioned, the donating groups will orient to the ortho-para position, while the withdrawing groups will orient to the meta positions. And we have one exception, which are the halogens. They will direct to the ortho-para even though they are withdrawing groups. This is the resonance that we have discussed. Notice the brackets that I have right here. These brackets arrange your arrange your groups according to their power of donation, which means that this group, the amines, the hydroxyl groups, and the oxide group are strong electron donating groups, followed by the acylated and the alkylated groups. These are the moderate electron donating groups, and finally the R, the alkyl groups. These are the weak donating groups. So how does this serve me? This serves me when I have two substituents on the ring. If the X belongs to this bracket and the Y belongs to the second bracket, then the electrophile will choose to go according to the Z and not according to the Y. On the other hand, if the Z belongs to this bracket and the Y belongs to this bracket, then the electrophile again will prefer to go according to the Z. Finally, if the Z belongs to this bracket while the Y belongs to that bracket, then the substituent, the third substituent, will choose to go according to the Y. It will go to the positions where the Y orient the next substituent to. Now, the halogens, as we have mentioned, even though they are electron withdrawing groups and they mainly withdraw by induction, and it's very rare for them to give electrons by resonance. However, they will direct to the ortho and para position because these positions place a positive charge on the, as you can see here, place a positive charge on the carbon directly attached to the halogen, which makes the halogen forced. It tricks the halogen and it forces it to give its electrons by resonance. Finally, the electron withdrawing groups withdraw the electrons, placing a positive charge on the ortho and para positions, as you can see here. And the stronger the electron withdrawing group, the more the electrophile will avoid the ortho and para positions of these groups. I'm sorry, in a previous slide, I have said that the electrophile will ignore the meta positions of the electron withdrawing group. I meant it will ignore the ortho positions of the electron withdrawing groups. On the organized slides, I will show you where the mistake was. So as I have mentioned, if you have two substituents on the ring, one is electron donating and the other is electron withdrawing, the new substituent will choose the positions related to the electron donating group. So it will choose the ortho and the para. The para is already locked, so it will choose the ortho position. If the ring is already carrying two electron withdrawing groups, it will try to avoid the ortho. This is where I was mistaken. I said that it will avoid the meta position of the electron withdrawing groups. No, it goes to the meta position of the electron withdrawing groups and it avoids the ortho position. So this is an electron withdrawing group. It will avoid the ortho and para positions. So it would avoid these positions. Let's put an X on them. And it will try to avoid the ortho and para positions of the nitro group, which are exactly the same. So it will have only one left position, which is this position. Now, if we have both groups as electron donating groups, it will choose between them according to the strength of donation of each group. As we have mentioned, this is a moderately donating group, while this is a very weak donating group. Remember the brackets in the slides where we arranged the electron donating groups according to their strength. So it will definitely go to the positions that are ortho and para to the moderate rather than the weak donating group. So it will choose these positions over those. It does not mean that it will not go to these positions, but this is a minor product. Your major product is the ortho and para to the amine part. Now we are done with the phenomena of aromaticity. What we will be discussing now are just some derivatives of benzene to apply. This is an application related to the benzene ring. If we place different substituents on the ring, how will we place them? How will we prepare them? And how will we react them? What are the reactions and what will be the influence or the effect of the benzene on the chain placed on it? Let's start first by the simplest, which are the alkyl groups. If you have an alkyl group attached to benzene, how will you introduce it? So this is your target substituent. You have an R on your benzene. How will you introduce it? So the synthesis. How can you synthesize it? You have two methods, either Friedel-Crafts alkylation by using alkyl halide in presence of a Lewis acid, starting from benzene, or you can use the Friedel-Crafts acylation if you fear a rearrangement process. This is step one, and then you will follow it by a Clemenson or a Wolff-Kishner reduction. What are the reactions of such a class? The reactions will be either what are the reactions? Before looking at these reactions, what are the reactions of an alkane? The reactions of an alkane is the substitution. You can substitute hydrogens of alkanes by halogens. So if you perform a UV substitution on the alkane, you will be able to replace one of the hydrogens on the chain. But which hydrogen? The rule here is that you are always replacing the hydrogen on the carbon directly attached to the ring. We say that you always replace the alpha hydrogen. Why is that? I will show it to you in a following slide. So if you perform a substitution reaction, you will always introduce the substituent alpha to the ring. So this is one reaction. Definitely you can perform all the electrophilic substitution reactions on the ring to introduce an electrophile to the ortho and para positions. And finally, the last reaction is if you oxidize such a compound using potassium permanganate, the product will be benzoic acid. And let's explain the first and the last point. Why did we introduce the substituent to the alpha carbon, and why did the potassium permanganate produce the benzoic acid upon oxidation of the alkyl benzenes. If you have a benzene ring carrying a group of carbons, a chain that is formed of more than one carbon, for example, such a chain. If you place a charge, no matter what the charge is, whether positive, negative, or a free radical, if you place a charge, whether a radical, a positive, or a negative charge on this carbon is immediately attached to the benzene, so the benzene will be performing a resonance with this carbon. In other words, it will stabilize the charge present on this carbon. However, if you place the charge on a far away carbon, if you place the charge, whichever charge you are placing on this carbon, the ring is far away. It cannot stabilize this charge. Okay, let's run a stabilization of a positive charge. If you have the positive charge on this carbon, then your ring will stabilize it and it will move the charge to within the ring and it will be carried within the ring, which is very stabilizing to any charge and thus favorable for this position. So this is why you actually introduce any substituent alpha to the benzene ring to enable the stabilization by resonance that can be performed by the ring. Now, the third reaction, which was the oxidation. Let me explain this point. If you have a carbon directly attached to the ring, and then this carbon is attached to, if you can see what I'm drawing, then I'm not drawing anything related to chemistry. I'm just drawing some lines, circles, a shape, which means that if you are having whichever substituent, we do not even care what the substituent is. We do not care what is attached to this carbon. My requirements are a benzene ring attached to the carbon. Then whatever is attached to the carbon does not mean anything to me. It can have monkeys attached to the carbon. I do not care. I do not care what is attached to the carbon. And I react them with potassium permanganate as an oxidizing agent, the whole thing will go away. All these drawings will go away and it will be changed to a carboxylic acid. So if I have something like that, and then another one, I'm expecting, if I oxidize with potassium permanganate, a dicarboxylic acid. And so on. No matter how many of these are present, they will all be oxidized. The drawings will go away. They will not be present in the final product, and the carbon directly attached to the ring will be converted into a carboxylic group. So this is how we deal with the alkyl benzene derivatives. Let's take a look at the second derivative, which is the alkenyl, which means that we will have a double bond in the side chain. This is my target compound. If you refer to the common names of the benzene derivatives, you will know that this is known as styrene. And if you remember in the limitations of Friedel-Crafts, when I told you if you need to synthesize styrene, your mind will definitely first of all think of reacting benzene with vinyl halide to produce the styrene, and this is a totally incorrect way of thinking because the bond between the halogen and the vinyl group is non-breakable, so you will not be able to synthesize this compound. So now we will see how to synthesize it. What you need is a halogen. How do we synthesize alkenes? How do you synthesize a regular alkene? you used to synthesize it from an alkane that has a hydrogen and a halogen, and you reacted with a strong base to eliminate the acid molecule, which is the hydrogen halide. So you will exactly do the same. You just place a halogen on the side chain. How do you, and then by a strong base like alcoholic potassium hydroxide, you will be able to remove the hydrogen chloride and get the styrene. How do you synthesize this compound? You can actually prepare it from the ethyl benzene by free radical halogenation or substitution of the alkane. And how do you synthesize this ethyl benzene? From benzene using ethyl halide in presence of Lewis acid. So you have just synthesized it from starting from a regular benzene atom, a molecule. So what are the reactions that can be done on such a compound? What are the reactions that are done on an alkene? First, you have the addition. You can add a halogen molecule. Just the known and regular reactions of an alkene. You can have addition of a halogen. You can have addition of a hydrogen halide. And as we said, you always introduce the halogen to the alpha carbon. Here you are not dealing with Markovnikov or anti-Markovnikov. You are dealing with the alpha carbon. You're adding the halogen to the alpha carbon, and you can oxidize this compound. We have mentioned that if you react anything that has a benzene in it and a carbon directly attached to the benzene, no matter what is present on this carbon, reacting it with potassium permanganate will give you benzoic acid. Okay, so these are the main three reactions of the side chain. Do not forget that you still can run electrophilic substitution reactions on the benzene. So this is the class of the alkynyl derivatives of benzene. The third class is the acetylenic compounds. We have the phenylacetylenes. So now we have the benzene carrying a triply bonded compound or a triply bonded side chain. How do we synthesize acetylene? What we did is that we placed two halogens and two hydrogens, and we eliminated both by alcoholic potassium hydroxide or by sodamide. Let's apply the same. What you need here is to have the two carbons both carrying halogens. And then you add alcoholic potassium hydroxide or sodamide to eliminate two molecules of the hydrogen halide. How do you synthesize this moiety? You can actually start from styrene and place a halogen molecule and a regular addition reaction in presence of carbon tetrachloride. As we have just mentioned in the previous slide, we said that you can add to the styrene. It's either you add a halogen, so you'll introduce two halogens to both carbons, or halogen halide, where you will introduce the halogen to the alpha carbon. So you have just added a halogen molecule. So you produce the dihalide, and then you eliminate the hydrogen halide using a strong base, producing the acetylene moiety. What are your reactions? Again, your reactions are either addition. You can add either halogens or you can add hydrogen halides. This is one reaction. And the second reaction is the oxidation using potassium permanganate. And again, you will get benzoic acid. You already have your requirements. A benzene ring attached to a carbon. No matter what is attached to this carbon, we do not care. You will still get the benzoic acid. And do not forget that you can still perform the electrophilic substitution reactions on the ring. The fourth and the last derivative, which is the benzyl chloride. A benzyl chloride is a benzene ring attached to a methylene group and a halogen. This is how a benzyl chloride will look like. A benzyl chloride is a very specific and special case because this halogen is attached to an aliphatic CH2. However, the whole compound is an aromatic compound. Removal of the halogen group, leaving a positive charge on the CH2, is highly stable and is possible because of the stabilization of the ring. Let's first look at how to synthesize such a compound. Synthesizing such a compound can be done in a very easy way, where you have a benzene which you will alkylate using Friedel-Crafts alkylation, using an alkyl halide together with a Lewis acid, followed by a UV free radical substitution of the alpha methyl group. This is one way of synthesizing, or you can just synthesize it from benzene in one step, where you use formaldehyde, HCl, and zinc chloride. In one step, you will introduce the CH2 chloro group. Reactions of such a compound are the reactions of the regular alkyl halides. If you remember when we were discussing alkyl halides, we had the halogen attached to a carbon, so the halogen was carrying a partial negative, the carbon was carrying a partial positive. You had three types of reactions: the formation of Grignard, which is possible here. You have the elimination reaction, which is not possible here because, as we said, to perform an elimination reaction, you have to have a hydrogen on the carbon alpha to the carbon carrying the halogen. This carbon has no hydrogen, so elimination is not possible. And then finally, the nucleophilic substitution reactions. You had the SN1 and the SN2. If you remember, we said that if you had a primary alkyl halide, which means that the carbon attached to the halogen is attached to one carbon, you should proceed through the through the SN2 mechanism, while if you had a tertiary, you should proceed through the SN1 mechanism. And we had a group of exceptions. We had group of exceptions to this rule, and the benzyl chloride was one of them. Please, if you need more details, refer to the video of the alkyl halides. We said that in case of benzyl chloride, even though it's a primary alkyl halide, since the carbon attached to the chloro is attached to one carbon, still it will perform a nucleophilic substitution reaction using the SN1 mechanism rather than the SN2, because when the halogen leaves, the carbon carries a positive charge. This carbon is directly attached to benzene. Accordingly, stabilization by resonance takes place by the ring. So you can substitute the halogen by any nucleophile, for example, a hydroxyl group, and another example is a cyano group. And you have all other nucleophiles that you can use to substitute the chloro group. The cyano compound, or the cyano substitution, is of special interest because the cyano group is a key functional group in organic chemistry, where you can hydrolyze them to produce the carboxylic acids, and you can reduce them to produce the amines. So now, looking at these benzene derivatives on the organized slides, we will start with the alkyl benzene, as we have mentioned.
you will have the benzene carrying an alkyl group. You can introduce it through a Friedel-Crafts alkylation or Friedel-Crafts acylation followed by a reduction. We said that the reactions are mainly two types of reactions where you can perform free radical substitution of the alpha hydrogen to the benzene ring, introducing a halogen, or you can oxidize alkyl groups on the benzene, giving benzoic acid. We also mentioned that you can substitute the ring in the ortho and the para positions by any electrophile. The second derivative was the styrene or the ethenyl or alkenyl derivatives, where you can prepare them through the alkyl benzene followed by free radical substitution of the alpha hydrogen and elimination of a hydrogen halide molecule using a strong base like alcoholic potassium hydroxide. The reactions were exactly the same as the reactions of any double bonded compound, doubly bonded compound. For example, you can add a halogen giving the dihalo compound. You can add a hydrogen halide and you can oxidize using potassium permanganate. When you add a hydrogen halide, remember to put the halogen on the alpha carbon to the benzene. It does not go to any other carbon. It will only go to the alpha carbon to the benzene. And this is the reason, because once you place a positive charge on the alpha carbon, the resonance will stabilize the positive charge by taking the positive within the ring and stabilizing it. The third derivative was the phenylacetylene. As we mentioned, you can synthesize them from styrene by first adding a halogen molecule followed by elimination of two molecules of hydrogen halide. Exactly the same way you synthesize acetylenes. Reactions were addition reactions and the oxidation of the side chain giving benzoic acid. Remember, in all previous classes, you still have the electrophilic substitution reactions of the ring. All of them can be applied here. Finally, we have the last derivative, which is the benzyl chloride. As we said, you can prepare it using formalin, hydrochloric acid, and zinc chloride. And the reactions of this compound are the substitution of the halogen. You can substitute with whichever nucleophile you prefer. We have here two examples, substitution with an OH and substitution with the cyano. And I would like to remind you again that the cyano is a very important functional group in organic chemistry, since it can be converted into two major and important functional groups, which are the carboxylic acids and the amines. I hope this video was of benefit for you in your studies of drugs that are aromatic and have different substituents on the benzene ring.